Good evening, everyone. I'm Dr. Josie Rawls, an astrophysicist at the University of York, and I'd like to welcome you to the winter webinar series. We've been bringing you cutting-edge research from the School of Physics, Engineering and Technology at the University of York to give you a glimpse of some of the range of exciting areas that our physicists and engineers are working on. But now over to tonight's event. So biomedical engineering applies materials, technologies, and tools to improve health, from developing diagnostic tests and drug delivery systems to designing surgical instruments and medical devices. Our speaker is Dr. Stuart Higgins, a UKRI Future Leaders Fellow and lecturer at the University of York. His research explores the role of bioelectricity in different biological systems and how it might be harnessed to help treat medical conditions. And with that, I will hand over to Dr. Higgins.
Thank you very much, Josie, for the introduction, and a good evening to everyone, and thank you so much for joining us on the webinar. And so, yeah, there's kind of two parts to this talk tonight. We're going to be talking a little bit around biomedical engineering in general and what it's all about, and the kind of basically the complexity of it, because there's so many different details and nuances to it. So I'll be giving you some of the highlights of that, and then I'll be telling you a bit about my little part of biomedical engineering and this slightly bonkers and new idea, well, actually not a new idea, quite an old idea, around can we heal people using electricity. So as I said, I'll give you this little introduction to the overview, and I'll link that to the kind of courses that are available here in the School of Physics, Engineering and Technology, and then I'll tell you a bit more about my own research. So, biomedical engineering, I mean, in itself, quite a jargony term. I find talks like this really fascinating because they say, okay, right, can you introduce your discipline, what you do? And I think, yeah, sure. And I start to write it down and I think, what's it actually mean? What do the words mean? It's quite complicated, and I'll explain that. But in essence, the way of thinking about biomedical engineering, it's this idea of taking engineering principles, the concept of using measurements and devices and techniques to help improve the world, and applying it in particular to medical and biological problems. But the difference here with biomedical engineering is that we're looking at healthcare purposes. How can we heal people? Now, what you might see when you look around are an awful lot of related terms, and they kind of fall under this umbrella of bioengineering. And it's kind of hard to draw a line between them. They're all kind of interlinked and mixed up. So we might talk a bit about some biomaterials. That's in essence the materials we create that are going to be in contact with a living organism or within a living system. We might think about bioelectronics, and at the end that kind of links to what I do, which is about how we create electrical devices that talk to living systems, or maybe measure organic molecules that are made by living things. And in terms of the disciplines, you have this whole area of biomedical engineering. You might have biochemical engineering, which is about how you, say, for example, take bacteria and use them to ferment and create a product. You might want to use them to help you produce a chemical. We do that quite a lot in our food production industries, but also in our other areas as well. Clinical engineering, looking at how we build devices for doctors, surgeries and hospitals and different operating environments. Tissue engineering, where we look at how can we encourage cells that maybe we've taken from our bodies and encourage them to go from just being cells in a petri dish back into being a complex organized tissue. Now that's particularly helpful when we're thinking about maybe we've injured ourselves or we've got a wound or something and we want to help our body build itself back again. So we might want to create a scaffold which cells could grow into. Again, a kind of biomaterial. These all terms are all interlinked. Neural engineering is very popular at the moment. It's looking at how we talk to our nervous system and how we talk to the cells that send electrical impulses around our body. And you'll see all these other range of terms, and it links into things such as medical physics and so on. So just to really reflect on the fact that while we're talking about biomedical engineering, it's a really interesting and complex and diverse set of different topics, and it brings in lots of different things from different areas. And really, it's all about this focus on healthcare applications. How can we create better technologies for better health? So that's a bit of spiel around the kind of definitions of the words, but what is it actually that biomedical engineers do? So I've picked out a few examples. It's not everything that they do because there's too many things to talk about, but it's some of the more interesting different topics that are available to us. So there's this huge area around biomedical imaging. So that particular photo is a MRI machine, a magnetic resonance imaging machine. essentially, they're all different ways and different technologies for looking inside the body. And different, you're often using electromagnetic radiation and passing that through the body and understanding and seeing different features within it. And so biomedical engineers might be looking at how we build better versions of those machines, how we use different kinds of physical effects and physical phenomena in order to understand and see different parts of the body. It might be about how do we take those devices, these imaging machines, and make them even smaller and miniaturize them so they could be inside the body as well. So as an example of this, within our School of Physics, Engineering and Technology, we've recently been joined by Professor Shihong Huang, who's a professor of healthcare engineering, and her work really looks at medical ultrasound and photonics. And so that's all about how you can use sound waves to image things inside living tissue. And her work looks at how you can create tools that allow us to see what's going on in the body better. Now, that might be for diagnostic purposes and allowing a doctor to make a more informed decision about what it is that's going on inside you. Or it could also be to aid treatment in the treatment of conditions, going in and seeing where particular tissues maybe need to be removed or repaired. The other huge area that biomedical engineers are involved in is this very nebulous topic of biosensors, and this can mean a whole range of different things. But I wanted to give you kind of an interesting, slightly unusual example. So the picture on screen is an example of a sweat sensor, effectively. So that little kind of transparent plastic square on one side contains a specially imprinted polymer that's sensitive to specific molecules that you can find inside the sweat. And so as these molecules come out, they bind with that polymer and it generates a little electronic signal. So most biosensors are around getting something to stick to something else and then detecting the signal, be it using light or electricity. And in this case, you can see it's electricity because there's a little circuit board stuck to one side of it. And so there's this whole world of biomedical engineers working on wearable sensors. Now, in this case, the sweat sensors actually have quite an interesting application. They're often very desirable in sports applications. So if you've got a kind of high-performance training environment and you want to be able to monitor how your athletes are performing, there's apparently quite a large market for devices that do that. But I guess we're also familiar with lots of other emerging biomedical wearable technologies. So in particular, I see quite a lot of adverts nowadays for things like diabetes monitors that kind of stick on patches that use different sensors that allow you to do continuous monitoring of your blood glucose sugar levels. And so there's a huge different range of devices that are really beneficial to have on the skin that allow us to sense different things. Another area that those biosensors can also be used is internally. So you might want to design a particular sensor that could pick up an electrical signal or detect the presence of a certain molecule inside the body. And again, a biomedical engineer would work out what kind of materials could be used to do that, and also the kind of materials that wouldn't react badly with the body and wouldn't create more of a problem by being there. That's often the biggest challenge. A few years ago, whenever you talked about lateral flow tests, you had to explain what they are to a large proportion of the audience. I think nowadays everyone's quite familiar with lateral flow testing. But again, in terms of biomedical engineering, this is one of the types of tests that we can work on and develop. So in this particular case, we've got a sample that will pass along a piece of paper effectively. And due to the particular chemistry that's printed onto that strip, it'll stick to certain substances that are present in that sample. So in the case of something like a COVID test, it's looking for a particular antigen, but actually it can be used for a whole different wide variety of applications. Now, the reason why we like tests like this is because they're very cheap and disposable, and they can produce in large numbers very quickly. That's the reason why this was such a popular test during the COVID pandemic. It doesn't require very complicated machinery. And so a lot of biomedical engineers look at that fundamental technology, this flow strip, essentially a piece of paper with a printed strip on it, and work out how you can take different chemistries in order to allow you to stick different things to it so it's sensitive to different tests. So in particular, in some previous colleagues I worked with, were looking at how you do this for things like HIV testing. How do you produce extremely sensitive tests for HIV and do it on a scale that can allow these tests to be produced very cheaply and affordably? Now, actually, the answer to that is really looking at the chemistry and how you use particular nanoparticles and how you stick them onto the surface. And so actually you're drawing from different subject areas there, thinking about the chemistry, thinking about how you print it onto the surface using an actual printer. And then also the kind of engineering of how do you encapsulate that device into a plastic unit and produce it and manufacture it in a way that's really affordable. And also just to say that there's a large other numbers of different biosensors completely, so that are based on electronic sensors. So for example, here in the School of PET, we have Dr. Chun Xiao, who's looking at microelectronic devices, essentially tiny little chips that vibrate at very high speed. And as certain molecules will come and stick to the surface of that little vibrating lever, tiny, tiny, thousandth the width of a human hair, then it will be able to change the way that the lever vibrates, and you can detect that as electronic signal. So again, biomedical engineers are all about looking and understanding how these different sensors could be incorporated into different applications depending on what's needed. Another big area, which again we're probably quite familiar with, around medical devices. So that image on the left is of a pacemaker, quite an old pacemaker I think in this one case, but that's a biomedical device. It's a device that contains a circuit board, and it allows it to deliver electrical impulses down the lead and to stimulate the heart muscle in order to regulate its behaviour. And I think there's somewhere in the region of about 500,000 pacemakers in the UK now. It's quite a large biomedical device that's now been adopted. And just to say again, in terms of biomedical engineering, it'd be looking at how can you make that device smaller? How can you make it less invasive? We're now reaching the domain where we can start to make our electrical circuits not out of metallic materials, but actually out of plastic conductive polymers. So these are flexible, bendy, sometimes gel-like materials that have the ability to transmit electricity through them. And so actually you start to move away from something like this, which is essentially a metal box with a wire on it, into something that's much more conformable and sits more easily on top of the tissue. And again, to highlight some of the more work that's happening here in the department, this is my colleague's work, Manish Chauhan, who's looking at soft robotics. So again, this is a whole field of engineering that considers how do you make devices that can move and manipulate themselves, but out of really squidgy materials, kind of gel-like materials. And the benefit from that is that then you can allow them to be implanted into the body, potentially without causing all of those kind of issues that you have if you have a hard object inside a living person. So in this particular case, this work, they were looking at how do you create a device that supports the diaphragm. If you've got a kind of irregularity with how the diaphragm moves your lungs up and down, you might need some support. This was designed to be an implant that could be placed inside the body and inflated and deflated to help the patient breathe. There's a whole different range of different devices like this, all linked to the field of robotics, and again, bringing in different aspects of biomedical engineering. Implants are another huge area. So that's a nice X-ray image of a hip replacement joint there. So we're incorporating things such as mechanical properties. What metal or what ceramic should that implant be made of? How do you stop it from? How do you stop bacteria from forming on the surface? How do you get it to successfully integrate with the bone around it? This has been a huge area of biomedical engineering challenges. And actually, at this point, you're thinking about, okay, what's the load bearing? What are the forces going through that joint? You're thinking about how can I manufacture that system? Does it have to be an expensive material? Could it make it out of a cheaper material? What if I could 3D print it? What if I could make it custom for the patient? And so all of these different questions and engineering challenges that get involved. Now, in some of my prior work, I was interested in this as well, because actually there's a question around how you texture the surface of an implant. And actually, even fundamental questions like, should that be a smooth surface or should it be a nanoscopically rough surface, actually has a huge impact. So one of the things that I looked at in detail was around this idea of what happens if you structure the surface and make certain spikes on it. And now we're in the field of biomaterials, another element of biomedical engineering. So this particular image here that you're looking at, we're looking down on a surface and it's covered with tiny spikes. And I say each of those spikes is smaller, about thousandth the width of a human hair, really tiny nanoscale spikes. And that weird dragged out thing sitting on top of it is actually a stem cell, a human stem cell that's sitting away there. Now, what we were looking at and what we were interested in was how do cells respond to really nanoscale changes in that surface? Do they behave differently if the surface is kind of atomically smooth? Do they behave differently if the surface has all these kind of different structures? And while this was quite fundamental, we're just kind of looking at what are the mechanisms that are turned on inside the cell when this happens. All of this kind of research informs the kind of more practical decisions. So when you're going to do that implant, what kind of surface should be on, what kind of texture should be on that surface? How can it best behave? Or what will give the best results? Similar kind of material, but a completely different application would be something like this here. So again, we're looking with a special electron microscope down at that surface. You're seeing lots of these tiny little nanospikes on the surface of this material, which is silicon is the material. And on top, each of those kind of rod-like structures is actually a single bacteria, E. coli. So a really super common bacteria. And so in this particular work, we're looking at saying, well, there was some data to show that could actually, these spiky, roughened surfaces have antibacterial properties. So considering, rather than saying we need to coat our surfaces with particular chemicals, or we have to use strong disinfectants, which have a real challenge around antimicrobial resistance, if instead we use this particular structure on the surface, would that really help? Now, interestingly, in our case, it didn't really help, because what you can see is happening here is that the bacteria are kind of stacking on top of each other. So even though the bacteria directly at the bottom might get prodded by these spikes, and that might disrupt their metabolic behavior, might disrupt their life cycle and ultimately kill them, actually there are enough bacteria around they can kind of just stack on top of each other. It doesn't really work that way. But again, it's a really fascinating insight into it. And actually you see this particular behavior in nature as well. So certain creatures, such as cicadas, on their wings have this kind of similar nanostructure pattern. Now for them it works. For them it helps shed dirt and also helps them keep a kind of antimicrobial surface on their wings. So that is this kind of a taste of all the different kind of ideas and complexity around biomedical engineering, and really just to share that it draws from a huge different number of different disciplines. So again, just picking a few, you know, we've got mathematics in there, we've got biology, we've got bits of medicine, we've got chemistry, we've got a whole range of computer science, which I didn't talk about. Whenever you're taking all of these complicated images using medical imaging devices, you need a lot of code, you need a lot of algorithms to understand what they're doing. And actually things such as machine learning and AI have made, actually one of the big areas where they have actually made a big difference has been in this understanding of how we can analyze those images. But it's also built on these fundamental ideas of physics, electronics, and then material science, which is the kind of essentially a study of materials, but also how you process them to get certain properties out of them. And I appreciate that if you're new to all this and you haven't seen biomedical engineering for the first time, you might look at that list and think, oh, blimey, I need to be an expert in all of those things. But that's not true. That's not really how the discipline works. A long time ago, I did a physics degree, and then I moved through different pathways in my research career and trained and retrained in different areas. And actually what happens is that you end up working in different specialisms, you become good at certain things, and actually you end up collaborating a lot. So biomedical engineering in particular is one of those subjects that really has a huge amount of collaboration. It brings together different people. You're continually working across disciplines. That can be quite challenging. At times you have to work out what's your shared language. How are you going to speak together, because you use different words to mean different words to mean different things. But that's also part of the fun. In my own work at the moment, I've spent the morning in some biology meetings, and you sit there kind of patiently going, I don't necessarily understand all of it, but I understand enough, and I know how to have a conversation with them that allows us to kind of move forward and come up with new ideas, and vice versa. So biomedical engineers and biomedical engineering use the principles of engineering to tackle real-world healthcare challenges. And I would say it's a really interesting field. If you've got lots of a wide range of interests, if you find yourself interested in lots of different subjects and not necessarily pigeonholed into one or two disciplines, it's a brilliant topic to look at. It is grounded in mathematics. There is always, you know, with all sciences, there's that kind of fundamental maths basis, but it's incredibly inclusive of other subject disciplines. So I've worked with people who are incredible artists, incredible skills in other areas of their lives, and they bring that kind of inspiration and those ideas into the process, because often you're problem solving really novel, complicated challenges, and you find that inspiration and ideas come from different areas. The whole field of biomimicry was around this idea that actually you could see different things from nature and take inspiration from nature and incorporate them into your engineering solutions. And I'm just going to end this section by talking a little bit around the undergraduate programs we have in the engineering side of things. So within the School of PET, we have different engineering families. We have the electronic and electrical family, and we have the engineering family. And within that, we have a medical engineering degree, and that includes modules on biomedical engineering, it includes modules on medical imaging, and all of those kind of different areas that would give a really comprehensive overview of all the different options that are available. So particularly, again, I haven't really covered it a lot, but we have huge amounts of different research into different areas and clinical applications, even things looking at how you analyze how people move to help diagnose certain conditions, and really wide variety of areas. So if that's the kind of thing that interests you, do have a look at it, and do have a look at the kind of modules and things that are around it as well. All right, so part two, the bonkers bit now, can we heal people using electricity? So this is quite new for me. So previously I worked a lot on biomaterials, and in the last year or so at York, we've been building this research team to try and tackle this really fundamental question. And actually it comes from history. It comes from a huge amount of history, in fact. So every time you talk about biology and electricity, there is a rule that means you have to put up a picture of frogs' legs. So this is a picture of one of Luigi Galvani's experiments. So Luigi Galvani was a scientist back in the 1780s and became famous for his experiments with frogs' legs. What he noticed was that if you touch the nerve of the frog and the muscle with two pieces of dissimilar metal, that the frog's legs would twitch. Which, when I first read it, I was like, well, how did you, what possible scenario did you end up in where you were doing that? Like, what happened in the lab that led you to that particular thing? That's a weird thing to be doing. Anyway, it says in the history books that it's because he observed his wife preparing a frog's leg soup, and as she was cutting through the frog's legs with a metal knife, he saw them twitch, and that's what gave him the idea. Which, I mean, that sounds reasonable. That sounds like a very normal thing to do then. I'll give him a pass on that. But what had actually been happening around this time, even before Galvani, was a huge fascination in the impact and the role that electricity played on living things. It was about the time that electricity had kind of been discovered. It's all new. Scientists have been looking at torpedo fish, which have the ability to stun their prey using electrical signals. It's probably fair to say that Galvani, at least in the kind of historical sense, is the one that's really captured the imagination and kind of spurned on centuries of further research afterwards. And so if we think about how electricity actually works inside living things, it's quite different to how it works in wires. So if I have my my phone charging cable, inside the bit of plastic is a couple of strands of metal, and metals have a sea of free electrons, and if I apply a voltage to one side of it, the electrons will move along that cable and transfer a current and charge. Now inside us there are electrons moving around, but primarily it's actually these ions that carry the charge. And so an ion is an atom or a molecule that's lost one of its electrons, so it's got this net positive or negative charge, and there are both positive and negative ions inside our body. Now what's fascinating is if you start separating those ions out, so if you've got a pool of kind of, I mean, effectively lots of kind of salty water around our cells, but you've put a cell membrane, a barrier that's from the inside of the cell to the outside of the cell within that solution, cells can actually start to manipulate the concentration of ions on either side of that gradient. And so within their structure, and this kind of very simple schematic shows the membrane, and then the blue blob in the middle is called an ion channel. And these allow certain ions to flow through to the other side of the membrane. And cells can even have pumps. They can actively pump ions against a gradient, for example. And so what you end up with is a concentration of ions on one side of the membrane and maybe a lower concentration on the other. And in physics, when you separate charges and you've got different densities of charges in different locations, you have a net electric field between them and you get a voltage. So actually our cells inherently have a voltage across them. Even every cell in our body has a kind of a voltage across its gradient. What's really fascinating is that it's not just at the cell level. Actually, as our cells organize into different tissues, they will assemble, and you can get even gradients of voltage occurring across tissues and across organs. And this is more prevalent in other organisms, such as these torpedo fish or different types of electric eel, where the electric field can actually surround the entire organism of the animal itself. So we have this inherent kind of bioelectric nature, and it didn't take long from Galvani onwards for people to start thinking, well, can we use this to heal people? So the picture on the screen is actually of an electrotherapy box, and specifically my electrotherapy box, which I have right here beside me. This is about 100 years old. It's an antique medical device. There are loads of them going around. Apparently there's made so many of them that you can find them on eBay quite easily. And what it essentially does, well, I didn't really know what it did when I bought it. I had to work it out. There's a place to connect a battery. There's this weird kind of coily thing. And then there are some, I'll get these out. Oh. copper rods that you hold on to. I'll move the slide on because I've got a better picture. And on top of the box is essentially a kind of very primitive circuit board with a kind of very lovely brass switch that's very satisfying to switch. And I thought, well, I've got a bit of engineering type. I did a bit of electronics. I can work this out. It'll be all right. I had not a clue. Had no idea. I looked at the bottom of that and went, I have no idea which wire is touching which wire, and it's all covered in gloop. And I didn't really want to start disassembling it to understand what was happening. So instead, I took it to the lab and I plugged it in. And so in this video, you'll see it attached to a power supply. And as I tune, you can hear an incredibly annoying buzzing noise. And in a moment, it will zoom in, you'll see what's happening. And what the video is showing is this tiny little armature, a little weight that's bouncing backwards and forwards between that black coil. And so it's essentially kind of a resonator. It's causing a kind of probably an electromagnet in there. It's probably charging up the electromagnet, dragging the bit of metal towards it. As the metal touches the magnet, it completes the circuit, discharges the coil, thing goes back again. It does this very fast. I was trying to understand how fast, and I thought I'll plug it into the oscilloscope and see. And an oscilloscope being the device we can use to see the frequency of the signals going through and see how different signals change with time. And it's oscillating about 2,000 times per second, which is that noise you can hear. And I was looking at this going, that's quite a big spike. And oh, that's actually, oh yeah, it's actually 40 volts coming off that thing. And I quickly turned it off. Because actually what this machine is capable of doing is taking a very, very small voltage, 1.2 volts, which is about the same as an AA battery, and turning it into some pretty large, meaty spikes. So this was all very fascinating, and I kind of, essentially if you were to grip onto these electrodes, you would feel a kind of pulsating effect. You'd notice there was something going on. It wouldn't be particularly strong, but you'd feel a signal. But at the time when these devices were made, people were claiming they could be used to heal a huge number of different things. So this is not from exactly the same era. It's from a few decades earlier, but it's gives you a sense of it. It's called the Electropathic Guide, and it would have been distributed with boxes like this. And it claims to cure all sorts of things from cold feet to cancer, which is quite the range of maladies. And it's easy to kind of dismiss this as pure quackery, and actually, obviously, it doesn't cure all of these things, and a lot of this is just kind of pseudoscience, and a lot of it at the time was people trying to make money from these devices. But I think it's also important to note that actually these devices weren't dismissed outright by the scientific establishment at the time. So this is Professor Benjamin Silliman, who provided a kind of endorsement for one of these particular products, and they were the first professor of science at Yale. Now, obviously, just because they're a scientist doesn't mean they were right, but it's just to say that it wasn't just instantly dismissed. Actually, there was a lot of kind of perception around how these devices potentially could work. What's fascinating is kind of what's happened since. So thinking back to the time of Galvani and thinking about how things have progressed, the knowledge has taken two different routes. So the work that Galvani and others started kind of led us down to this understanding of electrophysiology. So that's the study of how those ions move across membranes. It's about how the different voltages are established within living organisms. And so actually that's a really big area of research. It's what led to things like the pacemaker ultimately. It allowed us to understand how these pulses and how our nerves work. And it's led to all the kind of work on neural interfaces and looking at how we might heal spinal damage and different kind of effects that involve our nervous system. Fascinating area of research. But then equally, the kind of the electrical therapy as a treatment idea hasn't completely gone away either. It's still there in parts. Now, obviously, you can still go onto major online retailers and spend a lot of money on devices that claim to use electricity to completely heal you, which I would not recommend you do. But actually, even in the clinical space, there are actually medical devices that use both direct electrical currents and electrical fields to help, as they claim, stimulate healing behaviors. And one of the particular example areas is around things like bone fractures. So either around spinal fractures or around fractures that aren't healing properly. So let's say you've got a fracture and it's not joining up properly. It might have been pinned, it might have been connected together, it's still not working. The clinician in charge might prescribe you a course of treatment using a bone growth stimulator. It's essentially a device that is kind of like a wire basket. You put your arm inside and it applies an alternating electric field, and things happen and maybe it gets better. And so what's really fascinating is, I mean, I'm not a healthcare economist, but I have started to look into the different papers around this and the kind of medical studies, and the evidence is a bit mixed. It seems as though there is some kind of healing effect happening, but it's not very consistent. It's only under very specific circumstances, but it's not enough to outright dismiss the technology, if that makes sense. So I find it really fascinating. We've got some kind of mixed evidence that suggests maybe this is useful. We've got medical devices on the NHS that use electrical treatment and pulsing electric fields and to help heal certain conditions. But it's not clear, it's not very well understood. Now, at the same time as all this has been happening in the clinical space, the biologists have been busy as well. So the last few hundred years, as well as understanding all the kind of mechanisms around these ions that allow us to have nervous impulses that allow us to ultimately move our muscles and control them, there's been a much more recently a greater understanding of the role that different electrical processes play with inside living organisms. And I'm going to just pick a few very briefly for this particular talk, but also some of the more fascinating ones. So the image you're seeing on the right is actually of a particular kind of worm. And what's unusual about this particular worm is if you look closely, it's actually got two heads, one at either end. So this is a series of experiments carried out at Tufts University in the United States, looking at the effect of interrupting the electrical signaling across different organs, and in particular across whole organisms. So in this particular experiment, they were cutting worms in half, and this is a planarian, which is a classic model in scientific experiments because essentially it can regrow itself really effectively. So it has the ability to regenerate any missing part of its body, which would be an incredible superpower to have for humans to have. And it's kind of one of the goals of biomedical engineering is, could we encourage the body to heal itself and just regrow the bits that need replacing? This organism can already do it. It has those mechanisms in place. But what they showed is that by interrupting the electrical signaling, they were actually able to encourage the worm to grow a different part of the body than it needed or than it was planned to. So in this case, they could encourage it to grow two heads and it would carry on living as normal. You could even encourage it to grow two tail ends and it would carry on living. And it's relatively early days in terms of the experimental work, but what it really hints at is the role that the electrical signaling plays across the organism, because what they were doing was interrupting that electrical signaling and changing it and modifying it and showing how that then resulted in different parts of the organism regrowing. Fascinatingly, it also comes up in huge other areas as well, such as cancer. So cancer cells, similar to our normal cells, have this voltage across their membrane, but it's actually quite different. It's a bit more negative than the normal cells. And actually, as you see cells become cancerous, they change, and as they metastasize, their voltages change as well. So clearly, again, the role that all of this bioelectrical signaling is playing in cancer is incredibly important as well. And similarly, it's linked to things such as wound healing and cell movement. So when you cut yourself, what you're doing is effectively cutting through all those membranes that hold all the watery iron mix in different parts. And it all floods in together, and actually you end up changing the voltage that's across that part of the wound. And in fact, you get a voltage gradient towards the wound itself. And so certain cells are sensitive to that voltage and can use the electric field to navigate towards the wound and help regrow that particular area. So these are all really big, quite bonkers when you first approach them, kind of areas that we see the role that electricity plays. And what I find particularly fascinating is that we've got the biology on one side, which tells us something about the fundamental mechanisms, and it tells us that it's clearly electricity is playing a huge role in how biological systems operate. On the other side, in the clinic, we see medical devices that are claiming to have some kind of healing effect, but the evidence is a bit mixed and it's not quite clear under what circumstances. And we've got this gap between them. We've got this gap between the kind of fundamental science and the applied engineering. And so that's particularly what my group here at York focuses on. So we're part of what's called the complex interface team, and we're interested in designing engineering devices that allow us to both study the biology and study some of those effects that are happening, some of those electrical signaling effects that are happening, but in a manner that we can start to think about how we might be able to use that in a medical device. So trying to think about that translation from the fundamental research into a medical setting. So how are we doing that? Well, one of the particular areas that I'm really interested in are materials that are both sensitive to those ions, the charge carriers that we saw inside the cells that produce that voltage across their membrane, but are also sensitive to the electrons that we have running through our cables and in our computers. If we're engineering a device that is kind of mixing electronics and living things, we have to have some kind of layer in between that does that translation of talking between the two different worlds. And this is actually where one of my previous backgrounds comes in. So what this slide is showing on the left is actually a molecular structure of a particular plastic, two components in this system. And what's very interesting about this material is that it actually conducts electricity. Now, the reason why this particular cable is covered in plastic and the reason why plug sockets and things are made out of it is because they don't conduct electricity. They're insulators. About 20 years ago, 30 years ago, it was discovered actually you can even make plastics conduct electricity too. Not as well as a metal. You're never going to see them kind of fully replace metals in that sense, but good enough for certain applications. And so for a long time, I actually worked in the field of flexible displays. If you've seen any kind of recent foldable tablets or kind of smartphones that fold up, that was the kind of technology we were originally working on, because if you can make your circuit out of a plastic bendy material, then you can build a whole screen out of it and you can create these kind of very thin wearable electronics. I've got a little picture actually here, which is a bendy circuit I made about 10 years ago with these little kind of bluey blobs that represent the plastic material printed on top. But what's fascinating about those materials from a bioengineering perspective is that they're sensitive to the ions that we saw earlier in terms of inside and outside of our cells, but also the electrons that we find in our electrical circuits. So actually they're really good interface materials. They're a really good way of creating an environment that a cell can connect to on one side, and on the other side we can have our electronic circuit. So at the moment that's what we're trying to do. We're trying to look at how we can use materials like this and use different interesting chemistries by working and collaborating with chemists, and how we can apply them to interesting biological problems by working and collaborating with biologists, both here at York and across the country, and seeing if we can start to answer some of those fundamental questions. Now, it's still very early days, and we're just starting this research program, but I wanted to show you one final image before the end, which is actually showing you what 100-year-old technology looks like and what our kind of modern experiment looks like today. So on the right of the image, you've got my trusty antique electrical shock box, and on the left we've got, it's not quite the same, but it's basically the same, the modern equivalent, which is called a micro electrode array. So that little device in the corner right in the center, you can see there's a white square, and inside that white square is a circle, and inside that circle is a little green square, and essentially that's about 2,000-3,000 tiny microscopic electrodes, little pieces of metal, each individually connected to the circuit underneath. And what you can do with that system is that you can grow cells on top of it, and you can monitor the voltage that they're experiencing, and you can even send them tiny little electric shocks, and you can see what happens. And so what we're interested in our research group is looking at how we can change the surface of that chip, modifying it using things such as these interesting conductive weird plastics that we can engineer to make them more suitable for biological systems. And then seeing how we can modify and monitor how the voltages change across cells. So we're starting really small. We have to start at the cellular level before we can get any bigger. As we start to move up, we'll have to think about how can we take this device and this interface and then start to apply it to tissues and eventually to whole organisms. But I really like the juxtaposition of these two objects. We have 100-year-old antique technology, and then we have what 100 years of electronics development can do. That device on the left is essentially a kind of digital camera sensor that's been modified. It's very similar in sense. It's got pixels on it. And I just love this kind of comparison of what all of the electronic engineering, all of the advancements that have been made in the computational world now allow us to do and now allow us to achieve. So that's part 2 of my talk over. I'm just going to end by saying that if you're listening to this and you're, it's a cheeky advert actually, if you're looking for any jobs in this area, I am actually going to be recruiting soon for a technician and some research associates. So if any of this interests you and you're looking for work in this area, check out my website, which is complexinterface.com, and you can find out some more details. And there's a little bit more there about the kind of research that we do as well. Thank you very much for listening. I'm going to stop there and hand back to Josie, and I think we're going to have time for some questions.
Thank you very much, Dr. Higgins, for such an interesting and accessible talk. Just a quick question to kick things off in terms of what does a day in your life look like then as a biomedical engineer? Like, talk us through what you might do on a day-to-day basis.
A noisy 1-year-old that wakes up about 6 a.m. Get up, we do breakfast, do the nursery run, and then we come into the office. I'm trying. There is no. I mean, academia is one of those jobs where everyone goes, "No, there's no typical day," but it is one of the joys and the curses of the job is that it is so varied. So rather than give a vague answer that's not very useful, I'll talk about what I did today. I came in today, and at the moment I'm trying to buy some equipment for the lab. So I was looking at what kind of centrifuge I should buy, which is actually a spinny thing for separating out cells. So I do a bit of like working out what we need for the lab to help it run. I went over to a meeting with my biological colleagues and I listened to them talk about their cancer projects, not related to mine. I was there thinking, okay, well, this is very interesting. Could we apply this to our own work? I met with one of my students and we had a chat about their project and how they're getting on with their writing. And then, yeah, I was doing some preparation of an advert for a particular role we were recruiting, and then kind of preparing and giving this talk today. So that's a very honest answer, but it's a real mixture. It's not so much kind of always in the lab, as in, you know, by the time you start getting to this level in university, you're kind of mainly organizing teams and getting ideas together and bringing people together. But it's a lot of fun from the diversity of the role. You get to do lots of different things. It's a bit like running a small business sometimes, is what it feels like.
You mentioned that you came into it through physics. Is there a particular path you would recommend for people that are interested in becoming a biomedical engineer?
I think it has a real benefit from the versatility of it. So there are absolutely kind of bioengineering, and we have our medical engineering degree programs here, and they'd be an excellent start for doing that because they give you that grounding. If you look at the structure of those courses, you'll see a lot of similarity. It's grounding in mathematics, it's grounding in those core principles. So if you know from the off that that's something you're really interested in, then yeah, absolutely engage with those courses. But equally, if you're not and you kind of still prefer, say, physics or chemistry, there are so many routes into it as well later on. I've always worked in teams where we've never shared the same degree, if that made sense. People from lots of different backgrounds. I've worked with chemists, physicists, biologists, medical engineering, people with medical engineering degrees, people with nanotechnology degrees, and so on. So the real advantage of this topic is there are a lot of routes into it.
Great, thank you very much. So we've had a few questions on different types of machines that either claim to kind of alter your mood, or I know that TENS machines are used for kind of pain and things like that. Do you have any thoughts on the effectiveness of those types of machines?
I do. I'm going to be really careful because I've not studied a lot of these different machines enough. So again, one of the challenges I have to kind of focus on the particular area I'm doing. But I know that TENS machines, there's a reasonable amount of body of empirical evidence there that suggests they are really effective for a lot of people, and they'll often be recommended on the NHS as part of different treatment plans. I would say, you know, it's always worth doing a bit of your homework, and it's always just being careful to see what's out there. And whatever you do, especially when it's electricity and living things, just be really careful about what it is the electrical devices, whether it's properly regulated and being sold by a reputable retailer, so that you don't put yourself in any danger by exposing yourself to any kind of dangerous voltages as well.
Thank you. And in terms of kind of other machines that kind of are used for kind of treatment of depression and things like that, is there any evidence to suggest that these are effective?
I've not, so I'm going to be really careful because it's not something I've properly looked into. I've started to read a little bit around the clinical reports around those therapies. I'm not going to say anything just in case I get it wrong, but I seem to remember reading a few of the clinical guidance reports that were vaguely supportive of this. But again, if that's the kind of area, I would probably recommend that you talk to the qualified clinician in that area. I'm being really cagey because actually electricity has been used in so many different areas, and actually the history of electrical stimulation in human beings is really complicated and has quite there's a reason why figures such as Frankenstein and such form such a huge part of our popular culture. And so one of the things we try and do, and I try to do personally, is be really careful about what I claim to know and not know. So in our particular case, we're really interested in understanding how these particular effects on cells are happening, but how that then links to really complicated big organisms, i.e. humans, is a whole different area. And so I wouldn't claim expertise in that area. And that's the reason why I'm really careful about it, because actually in the past, it's been a bit of a dodgy area.
Yeah, I guess there's upsides and downsides to collaborating with so many different fields in terms of being able to answer particular questions on such specialist topics.
Yeah, and I strongly kind of believe as well, I need to be careful about, I'm not trying to claim that I'm an expert in certain things. I know my bit and I can do this little bit here, but actually we need to be, part of being responsible as a scientist is not trying to stretch too far outside as well.
Are there any known side effects of biomedical machines within the body?
More generally, yes, loads. So basically, this is one of the huge problems. Anytime you put something non-natural inside the body has a huge raft of mechanisms to kick it out again. It has a big immunologic response. So in terms of things like bioelectricity, classic example would be something like a what's called a neural cuff. So you've got long nerves running throughout your body that carry signals from your brain to various organs and to your muscles. And there's a lot of work focusing on how you can create little essentially wraparound collars that go around these nerves. If you do that with a piece of foil or something, the body goes, whoa, what's that there? A bit of metal, don't like that. And it will start to have an immune response, and it will start to effectively build up scar tissue around the cuff. Actually, another area where this is a real thing, if you've got things like deep brain stimulators, so one of the ways for managing the symptoms of something like Parkinson's, where you've got tremors, is to implant a electrode into the brain, which applies a little gentle electrical pulse. Now that's often a metal wire, and an uncoated metal wire will trigger a kind of scarring response inside the body as it tries to reject it. And what the scar is effectively doing is building up kind of inert material around the metal. And that's, in an electrical sense, is basically an insulator. So it's basically putting the plastic back on the wire and insulating it from the body. So often those electrodes have real issues that as they spend more time inside the body, you have to keep turning up the voltage to get the same effect. And at some point you can't turn the voltage up anymore because it's dangerous. So a lot of what different areas of biomedical engineering is doing is looking at how you can use these soft plastic materials to replace those metals, or at least encapsulate them in a way, or to tailor the surface chemistry of them so that the body accepts them more cleanly. And that's true in bioelectric devices, it's true of implants, it's true of anything that kind of goes inside or on the body.
Great, thank you. Been asked about some organic polymers that can generate photocurrents. Are there any kind of applications for this with sight?
Yes, there are a couple of interesting research groups looking at, can you essentially build a solar cell on top of a contact lens or on top of a tiny membrane that could go behind the eye? So the same materials that I was talking about, these plastic materials, have also been used in solar cells and have been used in, actually used in organic light emitting diodes, OLEDs, so OLED TVs. It's the same family of materials. And yeah, there are some groups looking at, could you actually engineer it so that where you've lost, I can't remember exactly, but I think it's the top layer of receptor cells that are sensitive to the light. So the eye's got quite a complicated structure. We have specific structures that sense the light and then generate a electrical impulse that travels down the nerve. And if that top layer has been damaged, if you could replace that with the equivalent of a miniature solar cell, where this organic material transforms effectively the light coming in into a little electrical impulse that then connects onto the nerve signal, maybe that would be a mechanism for restoring partial vision loss and things. So yeah, that's very much an active area of research.
Wow, yeah. Would you recommend any summer internships surrounding biomedical work for someone in secondary school?
Yes, I mean, if you're able to access them, the internships can be really valuable. I don't know of any schemes off the top of my head. I would recommend do check out the Generation Research Scheme hosted at York that can offer different opportunities. If you're thinking about being a biomedical engineer, what would be good? See if you could do some work experience in any kind of company, medical engineering company or pharmaceutical style company, would definitely be helpful. it would give you a real sense of how that side of things works, and that'd be really valuable. But again, I'm not really an expert on which internships to go for.
So I guess you've mentioned that from a biological side of things, some of these things like organ regeneration are kind of theoretically possible and seen in
Mm.
these kind of worm-like creatures. What are the main engineering challenges that kind of need to be overcome before it can become a practical application?
Loads. There's the well, there's the biology. Before you even get as far as the engineering, you need to understand the biology. So engineering is about taking the things and putting it together in a certain way to kind of solve the problem and create a device that does that. But if you don't know what the things it is that you're trying to manipulate to begin with, that's a hard starting point. So understanding the complexity of all the different interlocking biomolecular mechanisms that cause that in a really complex creature such as a human is the first part of it. And then actually for me, often I find that there's a I call it kind of a resolution problem. So if I want to make my bioelectronic device and I want to control lots of really small things, I kind of have to work out how I'm going to wire my device to all those really small things. So is it going to be, if I just have one wire, then I'm producing just a very coarse signal. It's just like on or off. And when actually we know that even nerve bundles are made up of hundreds and thousands of individual fibers, and the complexity of the tissues is really complicated. So in reality, what we probably need to do from an engineering perspective is miniaturize and come up with ways of binding our interfaces directly to the cells. And one of the ways I'm thinking of how we could do that is by actually taking advantage of things such as chemistry that will selectively attach to different cells that have different receptors on the outside of them. So kind of allowing the system to kind of organize itself and wire itself a little bit. So in terms of the engineering challenge, it's really complicated getting those electrical wiring into the right place, getting the signals into the right place with really high resolution, because everything's really small, is a real challenge.
So would you say we're kind of very early days of along that process?
In terms of things such as healing, yeah,
Yeah.
absolutely, very early days. Um, there might be easier ways along the route. I mean, a lot of these devices that you see in the clinics are very simple. They're just big wire cages that are applying an alternating field. They're doing things at a really big scale. My gut instinct at the moment is that the fact that there's mixed evidence, the fact that it's only seems to work in specific circumstances, tells me that the complexity of those devices doesn't match the complexity of the biology, if that made sense. That the device is a bit too simple for the kind of complex process it's trying to trigger. So that's my kind of instinct at the moment, is that we need to think more carefully about how we subtly stimulate the body in different ways.
Okay. And final question, kind of from a sustainability point of view, a lot of medical devices and things are made of plastics and things like that. Do you have any thoughts on reducing the environmental impact of medical products? I appreciate it's not directly linked to what you've been talking about, but you did mention that you're looking at using plastics, for example, instead of
Yeah.
some of these metal things. Is there a kind of sustainability side to things that is also considered in the kind of thought processes?
Yeah, and even more practical than that, how we run our labs, biomedical engineering and any biological work in its nature is often very wasteful. Like, we use a lot of kind of single-use plastics and so on in how we conduct things. So from a perspective of how we conduct ourselves, we're looking into how we can do a lot more plastic recycling. So often you're using a thing for experiment, you think, oh, it's contaminated now, we can't actually recycle it. But actually, could you find ways of cleaning it to actually then allow it to be recycled? So that's the practical side of it. In terms of the devices themselves, there is a whole, it's not something I work on, but there is a whole body of work that looks at resorbable electronics. So the idea that the system kind of can be reintegrated into the body, effectively washed away after its useful lifetime. So if you think about any kind of medical device, especially a device that's designed for healing, the goal is you put thing inside living person, it gets better, but then you want it to go away again, because otherwise you're left with things still inside person, which can be a problem, might require a second surgery or so on. So especially in the world of tissue scaffolding, and it's a little bit in electronics but less so, you see a lot of work done around the chemistry of the polymers, the plastics being used. And so you can design certain plastics in certain ways that after a particular time, either after a particular time, they will start to naturally break down into their constituent components. So a plastic is just a long chain of molecules that are repeating lots and lots of times. And if you can start to break those bonds, it will start to break down to little bits, and it can kind of effectively be washed out of the body. So that's one way of doing it. Or you can even be really clever and design materials that can be attacked by enzymes that are found inside the body. So the body itself will have a mechanism for naturally clearing out the system after a certain time point. And the skill comes in designing the chemistry in such a manner that the thing lasts long enough for the time you want it to, and then goes away again doesn't dissolve too quickly, doesn't dissolve too slowly. So that is a big area of work. A lot of chemists working in that area.
Great. And we just had a final question that we'll finish on about the kind of research process in terms of how you get approval to proceed with your research or even funding, especially on kind of cutting edge explorations that maybe involve, applications for the human body.
Yeah, so it has different layers depending on. So we tend to work, or we're only really focusing on cell work at this stage. And so we go through kind of, depending on the type of cells being used, and particularly if they're human cells, we go through a particular ethical review process. And that's something that goes to have ethics boards at the university. So anytime you want to do something, you have to say, this is what I'd like to do. Here's how it potentially affects different people, different systems. And that goes through and independently is reviewed, and you are confirmed whether you can do that work or not. The moment you start getting something where it's humans or patients involved, that process naturally and should get a lot more complicated. And so again, you have similar kind of ethical review processes for that. So yeah, it can be quite lengthy, but it's not the case that we can just do anything and stick anything into anyone. That's really not how it works. There are a huge amount of safeguards kind of built in. And it's really valuable with this kind of work to start building links to clinical partners as well. So starting to meet colleagues in the NHS and start to talk to them early on in the process, because that allows us to really understand some of the hurdles and some of the structures in place that can allow us to get those approvals. But also actually maybe start even talking to patients. So even though we're only potentially looking at cells and tiny things in petri dishes, understanding some of the lived experiences that patients go through early on in the process, understanding maybe the kind of discomfort they have from existing devices, can really inform the design process, even at this early stage, to really help you think, okay, if we design this thing, can I see a pathway to it actually being something that someone would want to use at the end of the day? Because ultimately, it's no good making something if it's so cumbersome or so uncomfortable that no one actually wants to use it.
Brilliant. Okay, well, thank you very much, Dr. Higgins, for such an interesting talk and for answering so many of our questions. So all that remains is to thank Dr. Higgins once again. So thank you and wish you all a very good night.
Thank you, everyone. Thanks for your time.